Hi, my name is Harlan. Welcome to the H Matricon Mechanical Engineering channel. Our topic for today is about heat transfer fluid systems for process heating. There are two common sources of heat in industrial processes. The first is steam, and the second is heat transfer fluid. Heat transfer fluid system refers to the use of diathermic oil to heat up a process that requires temperatures as high as 400 degrees centigrade. Diathermic means able to conduct heat, and heat transfer fluid is also called diathermic oil or thermal oil. Heat transfer refers to the thermal energy exchange between two materials due to a temperature difference. There are several advantages of using heat transfer fluid over steam systems for heating. The first is high energy efficiency. Second is high heat transfer rate. Third is simpler and thus easier to design. And fourth is non-pressurized system, well in the range of 15 pounds per square inch. Thus, it is a lot safer. Fifth will be better temperature control. And sixth will be quiet operation. And the seventh is non-corrosive. High temperature heat transfer fluids may be classified as synthetic oil, operating at temperatures as high as 400 degrees Celsius, and the hot oils, operating temperatures up to 300 degrees centigrade. And heat transfer fluids are commercially available in different brands. We have Shell Heat Transfer Oil S2, we have Petro-Canada Calflow AF, and we have Esotherm 500, Mobiltherm 600, Duratherm 630, Chevron grade 22, and Dowtherm T. Diathermic oil, high-quality mineral oil, resistant to thermal cracking, also resistant to chemical oxidation at high temperature, and high specific heat, and high coefficient of thermal conductivity. Fire safety, when using heat transfer fluid systems, depends on three parameters. You have flash point, fire point, and O2 ignition temperature. Flash point is when sufficient vapor is generated so that the fluid will flash when exposed to a source of ignition. Fire point, temperature at which sufficient vapor is being generated for the liquid to sustain continued combustion when exposed to a source of ignition. And O2 ignition temperature, the fluid at this temperature will ignite even without an external source of ignition. Thermal stability, the inherent ability of a heat transfer fluid to withstand molecular cracking due to high operating temperatures. Heat transfer efficiency, oils with higher heat transfer coefficients have greater abilities to conduct heat. Kinematic viscosity refers to the fluid's ability to flow. Viscosity decreases with an increase in temperature. Pumpability point, the temperature at which centrifugal pumps can no longer circulate the fluid. One example of a heat transfer fluid is Petro-Canada Calflow AF, operating temperature in a system typically at the range of 260 degrees centigrade, and we have a density of 44.7 pounds per cubic foot at a temperature of 260 degrees Celsius, flash point of 225 C, and fire point 240 C, and ignition point at 343 degrees centigrade. So we have a typical diathermic oil system, typical schematic diagram. Here we have the oil heater, and then it goes to the supply line after the heater. Goes to the different users, user number 1 and user number 2 here. Okay. User number 1 and user number 2. This is the supply line. And it goes back to the return line here, back to the filter, and then the circulating pump, which moves the fluid through the oil heater. So it circulates in this way here. And then we have your deaerator here, filter, circulating pump, and oil heater, and back. We have a bypass line here. We have a pressure control valve. So if the pressure here, differential pressure is high, it will open this pressure valve, pressure controlled valve, so that we will have the bypass line open. So circulation of the oil will not be disrupted. And you have here your temperature control valve. So if you need a higher temperature, it will allow more oil from the supply line to go through user number 1. Okay, and this one here is the expansion tank, so that in the event of temperature raises from the starting cold temperature start, oil expands, so it will be accommodated here in the expansion tank. And if you need to add oil into your system, the storage tank has its own pump to pump it through the return line. We have also a discharge tank, which accommodates the fluid when it will be used to empty the system from oil. In case you are going to do major maintenance, the line, and you're going to empty it, then you open this valve here, and this goes back to the discharge line, and which is then pumped back the storage tank. What are the key components? Let's discuss it one by one. The first will be oil heater. It may be electric or fuel-fired with an economizer to save on fuel usage. And it is sized based on the thermal load, the operating temperature, and the flow rate. It may be 2-pass, 3-pass, or 4-pass. The circulating pump, the operating temperature, the cold start temperature, and the properties of thermal oil. The pump motor is based on the cold start temperature and duty. So I have here a graph of Petro-Canada CalFlow AF heat transfer fluid that shows that as the temperature of the oil is raised beyond 100 degrees centigrade, the viscosity will be very low and it approaches 0. So we can see here that at lower temperatures, at roughly 50 centigrade, the viscosity is above 25 centistokes. So it is relatively harder to pump at this temperature compared to temperatures as high as 200 centigrade. The expansion tank. The expansion tank is vented to the atmosphere, and the expansion tank will be at the highest among the components. It has the highest elevation. Can we consider in sizing the tank the system volume? the initial fill of the tank, the operating temperature, and the coefficient of thermal expansion. And it is provided with an inert gas blanket so that oxidation can be avoided. Pipes and pipe connections. The pipes may be carbon steel, cast steel, or stainless steel. Avoid use of threaded fittings. Consider adequate thermal expansion and contraction. And of course, the proper use of expansion joints and flexible hoses are very important. Primary, secondary loop systems are needed. This setup is needed for tight temperature control. And second is the hot fluid is mixed with a controlled quantity of recycled cold fluid coming from the users. And multiple users can operate simultaneously at different temperature requirements. So we have here the configuration of a primary secondary loop systems, which is of direct return setup. So we will look closely here. We have the primary pump or the circulating pump, which forces the fluid through the oil heater to the supply line. And it is branched here to C for the first user and H for the second user, user number 2. And goes back here to the return line and to the aerator and back to the filter and the primary pump. And if you look at the users here, let us focus on user number 1. It has its own secondary pump. So when the pump is off, what will happen here is that oil will just flow through here from B, C, F, and G. Similarly, it flows also here from B, H, I, L. Go straight back to G and then to the aerator and so on. So if the secondary pump is not functioning, no oil goes through the user. When the pump operates, what happens is oil passes through the pump, it's sucked by the pump, going to the user and out into point F. The temperature control valve here controls the flow of this fluid out here. So what happens if this is, if we need hot oil, what happens is purely we have the hot oil coming from here going into your pump. So 100% of the oil going to the pump comes from the supply line coming from the oil heater. And once you need to reduce the temperature, we recycle part of that oil here. Instead of letting it through, we recycle it back to the suction of the secondary pump so that the temperature here will have a mixture of lower temperature going to your user. So that will be the type of control. And this is direct return. So we will take a closer look and analyze a direct return primary secondary system. So we can see here that the temperature at A is equal to temperature at B is equal to temperature at H. And the flow Q from A to B is equal to flow from B to C plus the flow from B to H. Okay, this is a junction at junction B. So the flow A to B is equal to the flow of B to C plus the flow B to H. Likewise, the flow from B to C is equal to the flow from C to F and the flow from C to D. And it is also important to note that the length of this line here from C to F and the length of this line here from I to L should be kept into a minimum. The reason for this is that this will have least resistance, so that if this has the least resistance here and the pump and the secondary pump is not operating, you will have the oil, all of it going through this line here. Nothing goes to the secondary pump unless it is running. So that's the reason why the distance between C to F and I to L are kept minimum. And we also notice that the length from B, C, F, G is a lot less than the length of the pipe from B, H, I, L, M, G. So what is the significance of that situation? If that is the case, that this line, this length of piping here is a lot less than this length of piping here, coming back to the return line, what does it mean? The oil flows to the least resistance. So there will be a lot of flow from B to C, B to G, compared to the flow in B to H. Okay? Let us compare it with the second setup. The second setup is the reverse return setup, wherein the supply line from A to B, so A here, the oil flows first into B, and then going to point G here also. So for the second user, it flows towards H rather. But notice that the oil first enters user 1, but it leaves first here. It leaves first the user number 2, so that the length of pipes from B, C, B, G, M will be the same as the length from B, H, and M. So the significance here is that more or less the flow from B to G will be equal to H to M, because the length of pipes are the same, the resistance, the flow resistance or the pressure drop will be the same because the lengths of pipes are the same. So we have the same flow. So let us take a closer look. Temperature of A is equal to temperature of B is equal to temperature of H. And the flow AB is equal to flow BC plus flow BH. And flow of BC will be equal to the flow of CF plus flow of CD. And similarly, as what we have previously discussed, the length of this line here, the common pipe CF and IL is kept to the very minimum, so that there will be minimal resistance to flow here, minimal pressure drop. So the flow will just be sufficient so that it won't go to the secondary pump at user number 1 and user number 2. And since the length of pipe from B, C, F, G, M is equal to the length of pipe from B, H, I, L, M, that is the same. So more or less the flow will be balanced from flow of BC to the flow of BH. Have the same. So the third configuration in the primary secondary loop system is the monoflow. What happens in this monoflow is that from the supply line, the users are arranged in a series arrangement. Unlike in the previous examples, we have a parallel arrangement. So we have the common pipe here, BE, common pipe FI. So if the secondary pump is not running, what happens is just oil just goes through here, goes through, circulated back to the return line. So let us try to analyze. The temperature of A is equal to temperature at B, but it is higher. What happens here? Okay. Temperature at A is equal to temperature at B, but temperature at B is greater than temperature of F. Why is it? Because after using the oil from B, it is returned back to this line here. So what happens is the temperature going out at this point will now be lesser than the temperature at B. And the flow from A to B is equal to the flow from E to F is equal to flow from I and J. That's why it's called, there is only one flow value, and that's why it's called a monoflow system. And as I've said, previously the common pipeline B to E, F to I is set at the very minimum in length, so that there will be practically negligible pressure drop from B to E and F to I. So if the secondary pump is not running, so all the oil will just flow through B, E, F, and I. Okay, I think the next video that I will be preparing for you will be about an analysis of an existing heat transfer fluid system used in the actual industrial process. So, and I hope you would watch my video tutorials. Thank you. Bye-bye now.